Hello, and welcome to the third lesson in this Euclidean geometry series. In this lesson, we build onto the theorems established and proved in the last lesson. We also use these theorems and Pythagoras' theorem to solve exam-type questions about triangles. By the end of this lesson, you should be able to prove that equiangular triangles have all their sides in proportion and are therefore similar. Prove that triangles with sides in proportion are similar and therefore equiangular. Prove the theorem of Pythagoras using similar triangles and solve some related problems. Have you got a pen and notebook handy? Good. Then it's time to say welcome to Kanya, who's helping me again today. Are you there, Kanya?
Yes, I am, Johnny. I'm standing by.
Good. Before tackling the theorems, let's see if you remember something you should have discovered before in your geometry classes, possibly in grade 9 or grade 10. Maybe you can help us, Kanya. Do you know how to determine the area of a triangle?
The formula, yes. Half times the base of the triangle times the height of the triangle.
That's right. We find the area of a triangle using the formula half times the base of the triangle times the height of the triangle. What about two triangles that are between the same parallel lines that have equal bases?
Their areas will also be equal.
Let's see if she's right. In this example, EF equals BC, and they are between parallel lines. So the areas of triangles DEF and ABC are equal. This makes sense because the two triangles have the same height if they are between parallel lines. And of course, if two triangles between parallel lines have the same base, then their areas are also equal. Here, both triangles have base BC, and they are still between the parallel lines. So their areas are equal. We are going to need this information a bit later in this lesson. For now, let's move on to a theorem. This theorem states that equiangular triangles have sides in proportion and are therefore similar. Read the theorem carefully for yourself. What is the given information and what do we need to prove? We are given triangles that are equiangular. That means that their corresponding angles are equal. This is all that we are given. The rest is for us to prove. We must show that triangles are in proportion. This will mean that they are similar triangles because we already know the corresponding angles are equal. This will make more sense if we look at diagrams. So let's draw what is given. Two equiangular triangles, and we'll call them ABC and DEF. Angle A is equal to angle D. Angle B is equal to angle E. And angle C is equal to angle F. Remember that the triangles are not the same size. Equiangular only means equal angles, but the sides can be different lengths. Now we can write this down as the given part of the proof. What do we want to prove using this diagram? We must show that the triangles are in proportion. One way to do this is to show that the ratio of side AB to side DE is equal to the ratio of side AC to side DF. With many theorems, each theorem makes use of theorems proved before it. We need to use the proportion theorem in order to prove the similarity theorem. To do this, we need to make our two triangles look like the triangles used in the proportion theorem. This calls for a simple construction on the bigger triangle ABC. If we construct a line GH on ABC so that AG is the same length as DE and AH is the same length as DF, then this would look just like the triangle used in theorem 1. So our proof begins with this construction. Now, what do we need to be able to make use of the theorem about proportional sides? We need to know if GH is parallel to BC. If it is, then the sides of triangle AGH will be proportional to the sides of triangle ABC. If we can get triangle AGH congruent to triangle DEF, then angle G would be equal to angle E, which is also equal to angle B, which means that GH is parallel to BC because corresponding angles are equal. Well, that shouldn't be difficult. Can you find 3 reasons for a congruency proof between triangle AGH and triangle DEF? Remember, for congruency, you need 3 corresponding sides equal, 2 sides and the angle between them, 2 angles and a side, or lastly, a right angle, the hypotenuse, and another side equal. We are given AG equal to DE and AH equal to DF. That's 2 reasons. What can we use for a 3rd reason? That's also easy. Angle A is equal to angle D. Fortunately for us, this is the included angle between the corresponding sides that are equal. Let's write this all down formally. Here goes. In triangle AGH and triangle DEF, AG equals DE because we constructed it like that. The same goes for AH equal to DF. The angles A and D are equal. They were given as equal. That gives us 3 equal parts in the 2 triangles, 2 sides and the angle between the sides. So we can write that triangle AGH is congruent to triangle DEF, side, angle, side. Look at the diagrams again. Why did we want congruent triangles? We wanted to prove that angle G equals angle E, so that we can say that GH is parallel to BC. Let's have a look. G equals E because the triangles are congruent. But B equals E was given at the beginning. So we know that B equals to G. Have a look at angles B and G on the diagram. Do you see that we can make a F shape using the parallel lines? So these are corresponding angles on GH and BC. So these lines must be parallel. And now we are able to make use of the proportion theorem. A line drawn parallel to one side of a triangle divides the other 2 sides proportionally. AG divided by AB is equal to AH divided by AC by the proportion theorem. Stop again and look at the diagrams. We cannot keep using G and H because these were points we constructed. They can't be part of the end of the proof. but we made AG equal to DE and AH equal to DF. So we can put these sides into the proportion statement. This takes us back to the original two triangles ABC and DEF. We have shown that their corresponding sides are in proportion. We started with their corresponding angles equal and so have proved that they are similar triangles. Let's have a look at the whole theorem again, one line at a time. Given triangles ABC and DEF, with A equal to D, B equal to E, and C equal to F, required to prove that AB divided by DE equals AC divided by DF. Construction is line GH so that AG equals DE and AH is equal to DF. The proof starts with congruency. In triangle AGH and triangle DEF, AG equals DE and AH equals DF by construction. Angle A equals angle D, given. Therefore, the two triangles are congruent. The reason, side, angle, side. Therefore, the remaining angles G and E are equal. But B is also equal to E, and so B equals G. These are corresponding angles. So GH is parallel to BC. Now we can say that the sides of ABC are in proportion because of the proportion theorem. So the ratio of AG to AB equals the ratio of AH to AC. Taking this back to triangle DEF, AG equals DE and AH equals DF. So triangle ABC is proportional to triangle DEF. In other words, DE to AB equals DF to AC. And so the triangles are similar. We have proved that the sides are in proportion, and we are given equiangular triangles to start. A good way to practice this theorem is to start with only the diagrams. Work out the given, required to prove, and prove from the diagram. The next time you try it, start with only the theorem statement. Work out what the diagram needs to be, add the construction, and then work out the required to prove and prove from the diagram. This theorem also has a converse. The statement of the converse is: triangles with sides in proportion are similar and therefore equiangular. So if you have two triangles and you know that their sides are in proportion, then you can prove that the triangles are equiangular. In this diagram, we look at two triangles where one is contained in the other. We are given that the sides are in proportion. This should immediately make you think of the proportion theorem.
I know. The sides are proportional. Then DE is parallel to BC.
Very good, Kanya. The sides are proportional. That means DE is parallel to BC. So angle D equals the corresponding angle B. And E also equals the corresponding angle C. Of course, angle A belongs to both triangles. So that means triangle ADE and triangle ABC are equiangular. Without writing out the proof for the converse theorem formally, we can already see how to prove it. See if you can write down the theorem and work it out on your own. You can check your proof against the one in your textbook. Let's look at an interesting way in which we use similar triangles to prove another theorem that you know well, Pythagoras theorem. You have used this theorem in problem solving for trig problems, geometry, and possibly in algebra too for the last few years of high school mathematics. Do you remember what Pythagoras theorem states? The theorem states that the square on the hypotenuse of a right-angled triangle is equal to the sum of the squares on the other two sides. So, if KLM is a right-angled triangle, the theorem proves that KM squared is equal to KL squared plus LM squared. This theorem has fascinated mathematicians for centuries, and it has been proved in several different ways. We are going to prove it using the proportion theorem and similarity. First, we need to construct a line LP that intersects KM at 90 degrees at P. Have a look at the diagram. Can you see a way of showing that the two small triangles KLP and LPM are similar to the big triangle KLM? If we can show that they are equiangular, then we know that they are similar. If they are similar, then we'll be able to use the proportions of their sides to work out the squares of the sides. Look at triangle LPM. We know that angle at P is 90. And so L2 plus M is 90 because of sum of angles in a triangle. So M must be 90 minus L2. But angle L is also 90 in triangle KLM. So L1 must be 90 minus L2. That's the same as M. And L1 plus K is 90 in triangle KPL, so K must be equal to L2. So have we found equiangular triangles? We certainly have. In triangles KLM and KPL, we have K is common to both. L and P are both 90 degrees and M equals L1. So these triangles are equiangular and therefore similar. In triangles LPM and triangle KLM, M is common to both. P and L are both 90 degrees and L2 equals K. So these triangles are equiangular and therefore also similar. Now, look at this carefully. We can use the proportion theorem to say that the sides are proportional. First, in triangles KLM and KPL, LM divided by KM equals PM divided by LM. In triangles LPM and KLM, KL divided by KM equals KP divided by KL. Now, we can use some of our algebra knowledge. If you cross-multiply these fractions, you get LM squared equal to KM times PM. And KL squared equal to KM times KP. We have come to something with the two shorter sides of triangle KLM squared. If we add KL squared and LM squared, we get them equal to KM times PM plus KM times KP. Taking a common factor of KM, we are left with PM plus KP in the bracket. Look at the diagram again. PM plus KP is the same as KM. So we have arrived at the theorem. KL squared plus LM squared equals KM squared. Here is the whole theorem again. We are given KLM and construct LP perpendicular to KM. We want to prove Pythagoras theorem that states that in a right-angled triangle, the sum of the two shorter sides squared equals the long side squared. We work out which angles are equal in the three triangles created and then show that the big triangle is similar to both the smaller triangles. Then we use the similarity to write down ratios of the sides that will help us towards our goal. When we cross multiply, we create squares on sides LM and KL, the short sides of the big triangle. When we add them together and simplify the left-hand side of the equation, we are able to show that the two sides squared are equal to KM squared. This proof of Pythagoras theorem using similarity is not complicated. You need to spend some time working out which ratios to use in order to get to the end result. Now, at least we have a few theorems on hand to use in solving some riders. Want to look at the typical question from a grade 12 exam paper?
Yes, please. I don't always know where to start.
First, list everything you know. Let's take a look at this diagram. What is given?
AQ is parallel to RT. The ratio of BQ to QC is 3 to 5, and the ratio of BR to RA is 1 to 2.
Yes. Have a good look at what information you are given. You should recognize which of these triangles have proportional sides based on the parallel lines RT and AQ. The first question is, if BT equals K, calculate TQ in terms of K. Can you identify which triangle you need to work in? What triangle has sides BT and TQ?
BT and TQ are part of triangle BQA.
Correct. BR and RA are also part of this triangle. Using this proportion theorem, what ratio can we say are equal?
Well, AQ is parallel to RT. So by the proportion theorem, we can say that BT divided by QT equals BR divided by RA.
AQ is parallel to RT. So by the proportion theorem, we can say that BT divided by QT equals BR divided by RA. Replace BT with K and put this equal to half. Then cross multiply, and what do we find?
TQ equal to 2K.
Here's the next part of the question. Calculate the numerical value of CP divided by PR. Identify the triangle that has CP and PR as one side. Are you going to use triangle BRC or triangle RTC? Be careful, the proportion theorem can be used on triangle RTC, but it cannot be used on triangle BRC. Do you know why not?
We don't have a line parallel to one of the sides.
Yes. So in triangle CTR, we know that CP divided by PR is equal to CQ divided by QT. To find the numerical value of this ratio, we can use any information that we calculated from the first question. BT equal to K and QT equal to 2K. That makes BQ equal to 3K. We know the ratio of BQ to CQ to be 3 to 5. That helps because that means CQ equals 5K. So now we know that CQ to QT equals 5K to 2K. And that's also equal to CP to PR. So we get CP divided by PR equals 5 divided by 2. And that answers the question. I think that's enough for today. But before we go, here is your task to do on your own. The first part of the task is for you to practice the proofs for the theorems that we have worked with in this lesson. The second part of the task is for you to answer this question. Given triangle STU with VR parallel to TU and V1 equal to V2, calculate SV and TU equals 35. RT equals 20 and SR equals 10. Make use of the equal angles, the parallel lines, and one of the theorems we have used in the last 2 lessons. A hint for this question: find the value of VU first. Please check our website to get the information needed for the task and other print-related information.